Learning how to program is one of the most important things you can do to increase your value to employers and also make you a much more valuable business analytics practitioner. So let's work through activity 3, where we go over the basics of writing for loops, while loops, and then also if-else statements. So question number 1 wants to explore just a basic for loop. So we're asked to assign a vector x to be a sequence of numbers, and there's a really easy way to go about doing it, but we're going to use a for loop just to illustrate how a for loop works. So although setting x to be equal to the sequence 5, 10, 17, etc., is easy with just this command right here, let's just run it. There's our sequence. We're going to use a for loop instead to define each element one by one. So what we'll do is we'll come up with some sort of sequence of commands that'll allow us to get some practice writing this for loop kind of from the ground up here. So when I write for loops, typically what I end up doing is writing the code that goes inside the curly brackets first. I get it working for a specific instance, and then I generalize it so that that code will work inside of a for loop. So let's imagine that I'm going to try to have it work for the fourth element in this sequence here. So I'm just going to set a variable equal to 4 here just to represent, all right, this is the position in the sequence that I'm going to get my code working for. And I'm going to write the relevant code here. Now the fourth number in this sequence is a 26. We notice that that would correspond to basically taking 2, 3, 4, 5, the number 5, the fourth number in this sequence here, squaring it and adding 1. So in this case, if I were to take the quantity I plus 1, which was that value 5, which I was going to square, and plus 1, you'll notice that I will get that value of 26, which I want as the fourth element in my sequence. So, all right, I have the code working for one particular element of my sequence. Now I just need to generalize it to have it work inside the for loop. So first thing I look at is what am I keeping track of? I'm keeping track of this quantity, and specifically I'm putting that quantity into a particular element of the vector x. So since I'm going to be putting stuff into the vector x, I need to start out by actually initializing x to be an object. Now there's nothing in here right now, it's an empty vector. I'll use the for loop to put in elements one by one. And so what do I need to do here? Well, I'm going to go ahead and write the for loop and then fill in essentially all the important parts of it. So what I need to do, what I need to loop over, are basically positions inside of the vector x. I want to go through the first element, then the second element, the third element, etc. So the thing on the right-hand side of the in, which tells me the values that I'm looping over, are just going to be the numbers, essentially 1 up through 9 here. It's a sequence that has a length of 9, and so I'll go through the first, second, third, fourth, etc. up to the ninth element in turn. Now I need to define an indexing vector, basically what's to the left-hand side of the in, and based on the way that I wrote my trial code, I'm just going to use the variable I, because I know when I enter into a for loop, what's on the left-hand side of the in, this variable gets automatically defined to be the first element of the vector that comes to the right-hand side, and so I've already essentially written this for one particular instance of that for loop. Alright, so now what do I need in the curly brackets? Well, I don't need this I left arrow 4 anymore because the variable I is going to be automatically set to 1, then 2, then 3, etc. as we progress through the for loop. However, what I do need to do is I need to store the result of this computation into the appropriate elements of my x vector here. So the first time through the loop, I is going to be equal to 1. I'm going to put into the very first element of my x vector the quantity I plus 1 squared, which would be 1 plus 1 or 2, quantity squared plus 1, which is that 5. Then, all right, do I need anything more? Well, I don't think so, because once I've done that operation, I run into the curly bracket, go back to the beginning of the for loop, I becomes left arrowed to the second element of this sequence, which is just going to be the number 2, and I'll be putting into the second element of x now the quantity 2 plus 1 squared, or 3 squared, 9 plus 1, which is that 10. So, all right, it looks like I'm in business. I've generalized that code so that it'll work inside of the for loop. Let's go ahead and do that and then essentially print out the values of x to confirm that indeed we have the sequence that we've been asked to generate. All right, question number 2 asks us to write a for loop over values of a categorical variable. So let's start from the ground up and figure out how we would write this code. So I'm going to load in the tips data frame, which is in the reg class package. Make sure the library reg class has been run. And what we're going to do is we're going to keep track of the average tip percentage for each day of the week in the weekday column of tips. Let's just get a preview of this. The first column is tip percentage, and we have our weekday column right here. Now, it turns out there's a really easy way to go about doing this. It turns out this function right here will accomplish exactly what we're trying to do, but we're going to do it the hard way with a for loop. The aggregate function will calculate some function of what's on the left-hand side of the twiddle, so some function of tip percentage, for each level of the quantity that comes to the right-hand side of the little twiddle. So for each unique value of weekday, we're going to calculate the mean tip percentage. Data equals tips is here just to let us know where those two values are living, what data frame they live in. So here's what our answer is going to be. Let's write a for loop to actually generate this answer on our own. All right, so my advice always is to come up with the code inside the curly brackets first. Try to get the code working for a specific instance of what we're looking at, and then try to generalize that so that it fits inside of a for loop. So in this case, I see that, all right, well, one of the days is Sunday, so I'm going to go ahead and just define a variable day to be called Sunday. And I'm going to try to get what the average tip percentage is for Sunday. All right, well, there's a few ways to go about doing this. The way that I'm going to do it is to create a subset. I'm going to call it sub in all caps. I'm going to take a subset of the tips data frame where the weekday is equal to, in this case, Sunday, but instead of hard coding Sunday here, since I defined the variable day to be Sunday, I'll ask for weekday double equals day here. So I'll run this and then just get a preview of it with head. I see that all the days are Sunday, and what I want to do is figure out what the average value of this column is, the tip percentage. So I'm going to just call that average TP, and I'm going to left arrow that to be the average value of that tip percentage column in the sub data frame. So if I define this quantity, I see that, okay, the average tip percentage for Sundays is 16.69. Looks like that matches up with what the aggregate function is letting me know, so I'm on the right track here. So these 3 lines of code are valuable. It makes it work for Sunday in particular. Now let's try to generalize this so we can loop over every day of the week and store the average tip percentage in a vector. All right, so how am I going to do this? Well, I'm going to start out just by writing the for loop, the skeleton of it, the for, the parentheses, the in, and then the curly brackets. I'm going to update what each of these things are going to be in turn. So the first thing I ask myself is, all right, well, what am I looping over? In this case, I'm looping over the levels of weekday, basically each day of the week here. And so on the right-hand side of the in, I'm going to put a vector that tells me what I'm looping over. And in this case, I'm looping over the values of tips $weekday. So here's my vector of values. I'll be going through Friday, Saturday, Sunday, then Thursday, and calculating the average tip percentage for each one of them. Now what goes on the left-hand side of the in is up to me, but since I already got my code working when I defined a variable day to be Sunday, why don't I go ahead and just reuse that variable name to the left-hand side of the in. So as we enter into the for loop, the quantity day will be left arrowed to the very first value in the vector to the right of the in. In this case, it would be Friday, and then it's going to run the code inside there. So we can see that the code that we've written essentially works for what will happen the 3rd time through this loop. So I don't need this day statement anymore. That'll be automatically left arrowed to the appropriate value as we work through the for loop. So what do I want to do at each iteration? Well, I'm getting a subset for that particular day and then keeping track of what the average tip percentage is. All right, but I need to basically be treating this as a vector. I'm going to create a value for the average tip percentage for each day of the week. So I'm going to store into a particular element, into average tip percentage, that value that I'm calculating here. So since I'm going to be referring to a particular element, I need to make sure that I've initialized that vector. I've made R aware that this vector exists before the for loop is started. So how am I going to refer to the position that I'm storing the average tip percentage into? I know the first iteration through the for loop, I'll be working with Friday. I want to put that into the first element of average tip percentage. The second time through the loop, I'll be dealing with Saturday. I want to put into the second position of average tip percentage, the average for that, etc., etc. Well, there are a few ways to go about doing this, as we covered in the notes. I think the most elegant way is with the which command. The which command will let us know what position into that vector that we're keeping track of the results we want to place stuff into. So how do we set up this which command? Well, here's the shortcut. What we do is we look back at the parentheses for our for loop and just reverse the ordering of the objects that we see and separate them by equal sign. So in this case, on the right-hand side of the in, we have levels, tips, $ weekday. We'll put that immediately after the which, put in double equal sign, and then take day and put that to the right of the equal sign. So that way, the first time through the loop, day is going to be equal to Friday. If we ask which levels tip $ weekday equals day, that's equivalent to asking, all right, which of the levels of the weekday column is equal to Friday, the current value of day, and that's the first element of that vector. So this will evaluate to just the number 1, and I'll be putting the result for Friday into the first element of average tip percentage. So there we go. It looks like I've generalized the code, and I'm just going to run it and see if my results match up. There's my vector of average tip percentages. That's what aggregate is telling me, and so looks good here. All right, so I'm going to move on to question number 3, which is another example of a for loop here. So in this case, we're going to do a bit of Monte Carlo simulation, basically see some what-if scenario by injecting a bit of randomness into the code that we are writing. So we're imagining that a stock's price changes each day by a percentage of its current value, and it's going to go anywhere from being down 10% to up to 11%. So on average, slightly positive trajectory here, and we're going to see what happens over the course of about 50 days here. So I have a little shortcut for basically how to update what the price equals if the change is, say, 7%. And so let's see what we're really being asked. We want to simulate the time evolution of a stock. It's going to start at $100 on day 1, and we're going to look at this over the course of 50 days. We want to know what the opening price is on day 50. And we're asked to let the vector prices contain the price history. So the first element of prices will be 100, and we'll figure out what the second element is with our for loop, with our code. All right, once we're done with that, we'll plot the price history with a special command, and the rest of these are just notes for how we can fill in some of the code here. All right, so how am I going to start out this for loop? Well, I'm going to ignore the for loop entirely and just get it to work, basically, say, for the second day of the simulation. I know what the opening price is on day 100. I'm going to write code that gives me the opening price on day 2 here. All right, so how am I going to do this? Well, I'm going to say prices 2, left arrow, prices 1 times the percentage change. Now, what is the percentage change based on the example that I gave? Basically, I need to generate a random number between minus 0.1 and 0.11, add that to 1, and then multiply it by basically the previous day's opening price here. So here's the previous day's opening price. I'm going to multiply that by 1 plus the result of running this command right here. So running this command gives me a random number between minus 0.1 and 0.11. I'll just run that command a bunch of times so you can see that happening. And so if I add 1 to that and multiply it by prices bracket 1, that'll tell me what the opening price is on day 2. So you can actually see that this is random if I were to run this code numerous times. I need to initialize prices to be 100 here. So it starts out on day number 1 at 100. You'll notice if I run this code a whole bunch of times, well, sometimes it goes up, sometimes it goes down, etc. So you'll actually get different results than I do if you were to run the same chunk of code because we're picking random numbers. All right, but back to the task at hand. I want to start out by writing the code that'll go inside the curly brackets, and so I've decided to figure out what the opening price is on day 2. The opening price on day 2 is going to be equal to the opening price on day 1 times its percentage change, basically 1 plus picking that random number between minus 0.1 and 0.11. So what I do is I can just run this command, and if I look at what's inside the prices vector, here's what it was on day 1, here's what it was on day 2. Just to get a little bit more practice with this, Let's try it for day 3. What would day 3 look like? Well, the opening price on day 3 is going to be the opening price on day 2 times the percentage change that happens on day 2. Same command, we'll get a different number out because we're picking a random number here. If I wanted it for day 4, well, you can see just a very simple amount of updating. The price on day 4 is the price on day 3 times its percentage change. So we've written code that actually works for quite a few cases. Now we just need to figure out how to generalize this and have this fit basically into a for loop. All right, so I'm going to go ahead and type in the key syntax for the for loop, the parentheses and the in, and then the curly brackets. And I need to ask myself, all right, well, what's going to go on the left-hand side of the in, and what's going to go on the right-hand side of the in? Well, what I want to be looping over are essentially the days in my simulation. I want to see, well, what's going to be the opening price on day 2, day 3, day 4, all the way up to day 50. So I'm going to loop through the values 2 up to 50, representing the day of the simulation. Now, what's on the left-hand side of the in is up to me. I can define any indexing variable that I want. I'm just going to use kind of my default choice of I when it's an integer, and we'll figure out what we need to change in the curly brackets to make this general. All right, so what we see basically is that, all right, if we were to enter in this for loop right now, I would be left arrowed to 2. Well, we already know how to figure out the opening price on day 2. We take the opening price on day 1 and multiply it by its percentage change. So if I just take this 2 and replace that by I, if I take this 1, replace that by I minus 1, well, then I'm in business here. Basically what the code inside the curly brackets is saying is that if I want the opening price on day I want to take the opening price on the previous day, day I minus 1, multiplied by the percentage change that happens that day. All right, so I've generalized that code. It's going to go through days 2 up to 50 in turn and figure out what the opening price is of the stock on that day. I can look at the values in that vector, and then I can plot this, the time evolution of the prices, with the command that's been provided to me. So in this case, it looks like awesome. I end up making really quite a bit of money here. So sounds good. All right, the bonus question asks us to essentially repeat this simulation a whole bunch of times to figure out, all right, well, what possible scenarios might I expect to see? So this is the time evolution for one possible universe for what happens in the next 50 days. But since all the percentage changes were random, if I were to run the simulation again in, say, another universe, I might get a very different looking trajectory. So in fact, if I just reuse this line of code, I can see that the trajectories can really look quite a bit different. Not every single instance do I end up making money. Here I make a ton of money. That's a great one. But in some cases, I end up actually losing money. It might take a few to go through, but here we go. I lost a bunch of money in this one. So this is interesting. All right, well, so after 50 days, what could I expect from the opening price on day 50? Well, I could essentially rerun this chunk of code and at each iteration, essentially keep track of what that opening price was on day 50. And that's going to be the job for a for loop. I want to repeat that same chunk of code, keep track of one thing about it, and keep doing it a set number of times. All right, so I'm going to go ahead and actually just dive in and write the skeleton of the for code here, because we've already written the code that goes inside of it, and just fill in the pieces. All right, so first of all, we're being asked to store the opening price on day 50 into a vector called final. So we're going to initialize the vector final to be just a blank vector here, and we'll put in the elements of that vector as we go through that for loop one by one. And it says to conduct the simulation a total of 5,000 times, put the opening price on day 50 in the appropriate position of final. So the first time we go through the simulation, we'll put into the first element of final what that opening price was on day 50. The second time we run the simulation, we'll put into the second element of final, the closing price on day 50, etc. All right, so that suggests a way to construct what goes inside the parentheses in this for loop here. Basically, we want to be looping through just the numbers, the sequence 1, 2, 3 up to 5,000, because we want to be doing the simulation a total of 5,000 times. So this code inside the curly brackets that we'll have will execute a total of 5,000 times here. Now it's up to me what I want to name the indexing vector here, what I want to have be left arrowed to the elements in the vector to the right of the in. And so what if I just use my default of I? I'll go with this. I'll explain why this is actually a bad choice in a second here. All right, so what code do I actually want to run each time I go through the curly brackets? Well, I want to conduct that simulation. All right, the formatting is getting a little bit weird. I'm going to go to Edit and then go to, where's reindent? Code, and then reindent lines. Looks a little bit prettier here. So I declare the opening price to be 100. I look at the time evolution up to day 50. And what I want to do is I want to store an element I here. First time through the loop, I is 1, then I is 2, etc. I want to store the very last value of the prices vector. And I'm going to do that just by doing tail prices 1. That extracts the very last element of the prices vector. That's an easy way to go about doing it. All right, now the for loop, as I've written it, is nested because I see a for loop inside of a for loop. And I need to be really, really careful when I start nesting for loops. Why is that? Well, I need to be extremely careful that the looping indices are different from one another. Otherwise, chaos is going to ensue because I is going to be continuously left arrowed to different quantities as it jumps in between the different for loops here. So because I've already written this chunk of code with I from 2 to 50, I'm going to keep that as is, and instead I'm going to change this from I to just trial. So in trial 1, we'll see the simulation. In trial 2, we'll do the simulation. And so I'll put into the trial element of the vector final the result of my simulation here, the closing price on day 50. All right, so we're good to go. We can run this code. It'll go through 1,000 different universes, evolve the opening price of the stock in each one of those to keep track of what happens on day 50. And what we're asked to do is look at a histogram of the 5,000 opening prices on day 50. So basically the results in those 5,000 different universes where we let the stock evolve. And here we go. We started out at 100. We see that, okay, the majority of times we make money. Not too big of a surprise because on average the stock price was a little bit positive, the percentage change at least. But some cases we actually lose money here. We're asked to figure out the proportion of instances where the stock closed below its initial price. So let's count that up. Let's look at the number of elements where we have final being less than 100, length which final less than 100 counts up the number of elements of final that are less than 100, and convert that into a proportion just by dividing by the number of elements in our vector final. So it looks like about a third of the time we expect to lose money according to this scenario. All right, moving on to question number 4, we're being asked to write a basic if-else statement. So the first part asks us to check whether a variable is greater than 70. If it is, define a quantity called weather as warm. If it is not, define weather as cold. All right, so how do we write an if statement? Well, we write the if, we put in some parentheses, we put in curly brackets, we write an else, and we put in some more curly brackets. All right, so what goes where? Well, inside the very first parenthesis, we put a logical condition that we're interested in checking. Here, we're asked to check whether a variable temp is greater than 70. So the condition I'm checking is, all right, is temp greater than 70? Now, the way the if loop or the if structure works is that if this logical condition is true, we execute the code inside the first pair of curly brackets. If it is false, what we do is we skip this pair of curly brackets, search for the else, and instead execute the code that goes inside the second pair of curly brackets. All right, so we're saying if the value of temp is greater than 70, if our logical condition is true, we need to define a quantity called weather as warm. All right, so I can do that just with the left arrow symbol. I'll define that as warm. All right, if it's not, if that logical condition evaluates to be false, I need to define weather as cold. So I can weather left arrow cold here. All right, so that doesn't look so bad. We're being asked to check our code for values of temp of 80 and 50 here. So let's set temp to be 80, run our if statement, let's set temp to be equal to 50, borrow this code here and run it again. So we know that if temp is 80, weather should be warm. If temp is 50, weather should be cold here. So after the end of that for loop, let's see what's contained in the variable weather here. So we'll run this first instance. I expect weather to be warm. It is. The second instance, we expect weather to be cold. It is. Great. All right, so for the second instance, we're asked to check whether the variable temp is greater than 70 and a variable sunny is equal to yes. If that's the case, it's going to define a quantity called day to be great. Otherwise, it's going to define the quantity day to just be okay. All right, so let's write our for loop. We need the if, we need the parentheses, we need the curly brackets, we need the else, and we need some more curly brackets. What's the logical condition that we're checking in this case? Well, we're checking to see whether temp is greater than 70, like last time, and we're being asked to check another condition simultaneously. We're being asked to see if sunny, some quantity sunny, equals yes. So how do I check more than one condition at once? If I want them both to be true, I separate the conditions with an ampersand symbol. So I'll check to see what's inside the sunny vector. I'm checking equality, so I have double equal signs, and I'm looking to see if this is equal to yes. So if the temperature is 70 and sunny is equal to yes, then I'm going to define a quantity day to be just the word great. All right, if it's not the case, I'm going to define the quantity day to just be okay. So if this evaluates to false, I go to the else statement, execute the code inside that set of curly brackets. I want to set day to be equal to just okay here. All right, so seems airtight. Let's test our code here with combinations as follows. So what if we had temp equal to 75, and I'm going to write another line on or another piece of code on the same line, separating it by a semicolon here. We're going to have sunny be equal to yes, because the weather is sunny here. We'll check that and we'll print out what day is. All right, so in this case, temp 75, sunny is yes, day should be great. It is. All right, let's change what I'm testing here. Temperature is now 65, and it is sunny. So it's just an okay day. It is sunny, but the temperature is not above 70, so I expect day to be okay. And it is. All right, another test case. We're being asked to check whether the temperature is 78 and sunny is no in this case, because it's cloudy. We should expect day to be okay. It is. And then finally our last case, if temp is 55 and sunny once again was no, because it's rainy out. If we run our code, we expect the day to just be okay. And indeed, that's what we find. All right, so question number 5 pushes us a little bit further and asks us to write a more complex if-else statement, basically a nested if-else statement that's going to consider the value of x and classify it into one of three things, either big, medium, or little, depending on the actual value of x here. All right, so what we're going to do is we're going to start out by writing out the if-else statement and filling in the pieces here. So we're being asked to consider the value of x, and what we're first asked to do is if x is 25 or more, then a variable y should be set to big. All right, so if x is 25 or more, so greater than or equal to 25, what do I want to do? Well, that's going to go inside the first set of curly brackets. I'm going to set y to be the word big. All right, so if that's not the case, if x is less than 25, what do we do? What do we do in this else statement? Well, we're being told that if x is between 10 and 25, then the variable should be set to medium. All right, so how can we write that? Well, if we end up in this else statement, we know that x is at least 25. So we don't have to actually specifically reference this 25 anymore because we know that x is going to be less than 25. In order for x to be between 10 and 25, we need to check to see if x is bigger than 10 here. All right, so the only way we can end into this else statement is if x is less than 25. If x is also bigger than 10, then we'll have x between 10 and 25. So another if statement, so we'll write our if and else clauses. What are we going to do if x is between 10 and 25? Well, we're going to set that variable y to be medium. Okay, sounds good. There's still more though. If x is 10 or less, then the variable y should be set to little. So, all right, if x is less than 25, we go into this else statement and execute all the code that's inside the curly brackets afterwards. We check to see if x is bigger than 10, and if it's not, if x is 10 or less, Well, we skip the first pair of curly brackets after this if and go into the curly brackets in the else statement. In that case, we're being asked to set y to be equal to little, and there we go. So nested if statements, I'm just going to start deleting things. And actually, since this line of code isn't all that long, I'm going to fit everything just onto the same line here. So it looks fairly complex. It helps to kind of parse this in pieces. But let's check to see if our code works. So we're being asked to see if our code works for values of x of 35, x of 16, and x of 2. We know we should get big, we should get medium, and we should get small out for these three test cases. All right, so let's move that first test case up there. We'll print out to see what y is, and then move on to these other two test cases. All right, so x is big. Y should reflect that. It does. X is medium in this case. Does y reflect that? Yes. X is small. Does y reflect that? Yes, it does. It's set to little here. So success. All right, question number 6 actually pushes us even a little bit further and has us explore a command called if-else, basically a shortcut for combining a for statement with an if-else statement. So what we're going to do is use the tips data frame and create a categorical variable whose entries are big or small, depending on whether the tip percentage is at least 20. All right, so if we were going to use a for loop to do this, and we're not going to do this, here's how we would do it. Well, we'd come up with a test case that works for a particular entry of the column of tip percentage, and then generalize that so that it works inside of a for loop. So what we could do is something like this. Is we could say, all right, well, let's imagine we're looking at row 13 right now, or 14. Let's write the code that gets us there. So basically, if the value of tips $percentage, the position inside that column, if that is at least 20, then we're defining some sort of categorical variable whose entries are big or small. So I'm just going to call it tip type. Why not? That's going to be big. Otherwise, it's going to be tip type is going to be small. All right, so this would take care of row 14 here. Let's look to see what tip type is equal to. It says small. What is the tip percentage in position 14 here? 16.3, less than 20, so it is small here. So if I wanted to generalize that into a for loop, well, I would look at what I'm storing here, basically big or small, into a quantity called tip type. Since I want to do this for each row of the data frame, I need to initialize this quantity as a vector, actually, and start putting in the elements one by one as I go through a for loop. So I type in for, put in the in statement, type in the curly brackets, and then update my code. What am I looping over? Well, I'm looping over each row of the tips data frame, row 1, 2, 3, 4, etc. So the values in the vector on the right-hand side of the in are going to be just the integer sequence 1, 2, 3 up to the number of rows of tips. It's up to me what I want to call the indexing variable, what comes to the left of the in, but since I wrote my example code to rely on a quantity called I, it was set to 14, I'm going to call that to be I inside the for loop. So as we go into the for loop, I is going to be left arrowed to 1, the code inside the curly brackets runs. Then I becomes left arrowed to 2, the second element of this vector. The curly bracket code is going to run, etc. So I no longer need that. I is automatically defined as we go through the for loop. If the ith value in the tip percentage column is at least 20, well, I want the ith element of tip.type to be big. Otherwise, I want the ith element of tip.type to be small. So if I were to do this, well, I could look at the values of tip type, and they're all either big or small. So that's one perfectly valid way to do this, but there's a shortcut because you'll notice that I'm basically nesting an if-else statement inside of a for loop. Now this happens so often that there's this special command, if-else, that does this for me automatically. So how does this work? Well, let's see. If-else is a function that takes as its first argument the logical condition that the if statement uses. So what am I looking at for my logical condition? Well, I'm looking to see if the tip percentage is bigger than or equal to 20. I'm basically going through the values one by one in the for loop. The first argument is just, give me the whole vector of values, and I'm going to check them one by one at a time. So the first argument is the logical condition for each of these checks here. The second argument is what you want to be the result if that logical condition is true. And in this case, we would like this function to return the quantity big, because if it's 20 or bigger, that tip is called a big tip percentage. Otherwise, it's going to be small. So if else is going to return a vector of values. It's going to consider each element of the first vector that's passed to it. It's going to look at the logical condition. It's going to go through element by element, and in the corresponding element of the output, the result is either going to be big or small, depending on if the logical condition is true or false. This first one if it's true, this second one if it's false. So if I run this, I'm going to get the exact same vector as what this for loop gives me. So, all right, I can just save this to tip type and be done with it. That accomplishes the exact same thing as the for loop that I have down here. All right, now it's not quite a categorical variable, however, because right now it's a character vector. It's not keeping track of the levels as you saw. I can convert it into a categorical variable just by using the factor function. So now if I do that and do a summary of tip type, it'll actually give me a frequency table of how often I saw big and small tip percentages. All right, so this is the equivalent way with a for loop. So we like this as a shortcut. It's much more efficient. All right, question number 7 is kind of interesting. It's going to ask us to find a secret code. So on Blackboard, there's an environment file called activity3.rdata that we're going to load into our working environment. So what I'm going to do is actually clear out our working environment so that R knows nothing, and I'm going to load in this rdata file. So that loads in the environment of a previously saved session, and we see that we have a function called crack here. So crack is a function that takes as its argument a number and returns either true or false. There's only one value, one integer that it's going to return true for, and that's the secret code for this assignment. The secret code is 5 digits. The first digit is not a 0, and we want to crack the code here. All right, so let's try out 49824. Notice if we run crack with that argument, it turns out false. That is not the secret code. All right, so let's do this one of two ways. Let's do a while loop first. So one thing we know about a while loop, if I just write out the skeleton of a while loop, is what's going to happen is that it's going to execute the code inside the curly brackets until the logical condition inside the parentheses becomes true. So technically what happens is that R is running code and it runs into the while loop. It checks to see if what's inside the curly brackets is true. If so, it executes the code inside the curly brackets, goes back to the logical condition into the parentheses, checks to see if it's true or not. If it is true, it continues to evaluate the code inside the curly brackets. All right, so how could we do this in a while loop? Well, what we could do is, since we want to go through systematically and methodically every possible combination that it could potentially be, why don't we create a quantity called code. Let's start it out at 10,000. That's the smallest value the code could be. And we'll look to see if the crack function, if we use that code, let's see if we just run this right now. While the crack code function returns false, I need to keep doing something. So code is 10,000 right now. Crack code becomes false. I'm checking to see, is false equal to false? Yes, it is. So I'm going to run the code inside the curly brackets. What do I need to put in here? Well, basically I want to try the next higher code. I want to take the current value of code and just increment it up by 1. All right, so to manually kind of talk about what's going on with this for loop, code starts out as 10,000. We check the logical condition inside the while loop. We find that it's true because crack code does indeed equal false. So we take the current value of code, which is 10,000. We add 1 to it. We redefine that to be the value code. And we see, all right, is this a secret code? Nope, it's not, because crack code is equaling false here. So false equals false, that's a true statement, so we increment it up by 1. So all right, I can run this while loop, and it'll keep going until it finds the case where crack code equals to true. Once it does that, it'll skip what's inside the curly brackets. So if I just print to the screen, what's the code? That's going to be my secret code. I can verify that that's the case by just running it manually here. I see that's the secret code for the day. All right, well, what's another way I could go about doing this? Well, I could do this with a for loop as well. So what's my recommendation for writing a for loop? We'll write the code that's going to go inside the curly brackets first, and then generalize it so it'll work inside the for loop. So, all right, what do I really want to be doing inside this for loop? Well, I want to be checking to see if crack code is true. So I could basically set up an if-else statement. Got to get curly brackets there. That basically says, all right, if crack code is equal to true, I'll put that the winning combination is that value of code. Otherwise, all right, well, I don't actually have to do anything here. If I don't find it, well, I don't have to do anything at all. So I should probably actually give it a test value here, like code is equal to 10,000, or 10,000. If code is 10,000 here, is crack code equal to true? It's not. Winning code is not going to be set to code. Instead, it would go to what's inside the curly brackets of the else statement. But in this case, we don't actually need to specifically say what goes into an else statement, because the for loop will automatically increment up the code that we're checking if we set up the for loop correctly. So how could we do that? Well, let's wrap this all inside of a for loop now. Basically, what we want to be doing is looping through every single possible valid combination. So that's just the sequence, 10,000 up to 9999. We use the variable code here to kind of write the trial case. So I'm going to have my indexing variable be called code. All right, so let's read it. So we go into this for loop. Code is going to be left arrow to 10,000. If crack of 10,000 equals to true, in other words, we found the secret code, it's going to set the variable winning.combination to be that value of code. Otherwise, we don't need to do anything, because by the time we get to this ending set of curly brackets, we go back to the parentheses in the for loop, and what happens is that code becomes the second element of this vector. Code will automatically be left arrowed to 10,001. All right, so I can run it this way. Run my for loop, and eventually I'll have found the winning combination. I can print that out, and indeed it's 14524 here. So two ways of accomplishing the same thing. All right, question number 8 actually demonstrates a pretty interesting function called curve, which allows you to visualize what any sort of mathematical function really looks like. So here we have a mathematical function that takes x and returns x to the fourth minus 3x cubed plus 2x squared minus x plus 10. All right, kind of a funky polynomial function here. We might be curious to know, what does that look like? Well, we can use curve to find that out. So here's a line that defines that function. We'll learn more about that next week. And curve will take the name of a function and where we want to see a plot of, so from 0 to 1 here, and it shows you what that function looks like. All right, our goal in question number 8 is to figure out where is this function minimized. Maybe this function gives us the cost of some sort of business process if we set the variable x to be equal to one of these values, and we want to minimize the cost here. So specifically, what we're interested in doing is looking at values of x of 0, 0.01, 0.02, all the way up to 1. We just want to consider these 101 values and figure out the value of x that minimizes our function. We can see that it's just a little bit above 0.2, so which value minimizes this? All right, so I'm asking you to do this in a very particular way, just to get some practice with a for loop here. So what we're going to do is as follows. We're basically going to start out by defining a value called minimum, which is going to be the best value of our function f that we've seen so far. And we're going to set it equal to 1,000 right off the bat. Notice that the values that we see between 0 and 1 are all less than 10, so as soon as we start searching around, we're going to immediately run into a function that's going to be evaluating to a number that's much less than 10,000. So we'll update the best value we've seen so far immediately. And then what we're also going to do is define a variable called best.x, and that's going to keep track of the value of x that gave us the smallest value of that function so far. We're going to start out by setting it equal to -1 because, all right, as soon as we start out searching, x is going to be equal to 0. We're going to get a better value of our function than that 1,000, and we'll update that best.x value up to 0 immediately here. All right, so how are we going to do this? Well, we're going to do this within a for loop. Basically, we're going to go through systematically through each one of these values of the sequence here, try out all these values of x, see what value of f that results, and then find the value of x that results in f being a minimum here. All right, so let's do this. So we've defined our function f. Let's define that variable minimum and best x here. Now let's go ahead and write our for loop. Now normally, I always recommend writing the for loop for a particular instance than generalizing it, but I think we've had enough practice that we can just dive right into this one. So to the right-hand side of the in, I want to write a vector of values that I'm looping over. Now in this case, I've said that I want to be trying out values of x from 0 to 1 in increments of 0.01. So the values that I want to be looping over are the values inside this sequence right here. If I just look at that sequence, I can see that it is 0 to 1 in increments of 0.01 here. All right, so I need to give my indexing vector a name. I'm just going to call it x here because basically that's what I'm trying. I'm trying values of x from 0 up to 1. All right, so what do I want to do at each iteration of the loop? Well, I want to see what the function value is for that value of x. If that's a better function value than what I've seen before, I want to update the value minimum to be the new value of that function, and I want to update that value of best.x to be the value of x that gave that minimum. So, all right, if I get a better value of my function at this value of x, I need to do something. So if f of x here, putting that current value of x into the argument of my function f, if that's smaller than the best value that I've seen so far, well, all right, what am I going to do? One thing I'm going to do is I'm going to update the best value that I've seen so far to be exactly what this current value of f is, the value of f evaluated at x. And then I also, because I've discovered a new best value, I want to update what the value of best x is, basically the current value of x that I'm searching through in my sequence. So how is this read? Well, we start out by defining x is going to be left arrowed to 0. I'll look at what f is evaluated at 0, and I'll look to see is that better than the current value of the minimum. It will be, because I can see that at 0 this is just about 10 here. So we'll execute the code inside the curly brackets just to the right of the if. We're going to redefine minimum to be that value of x, the better value, and we'll update our best.x value to be keeping track of the best x that we've seen so far, the one that gives the smallest value of f. Now, what if this statement is false? What if that value of f is not better than the best I've seen so far? Well, I don't need to do anything. I don't need to update anything at all. The only thing I need to do is move on to the next value of x. So in this case, even though usually if-else statements come together, I'm not doing anything inside the else statement, so I can just delete it. So we run what's inside the if statement. We'll run into the curly bracket that ends our for loop. So we go back to the beginning and then try out that next value of x. So there we go. We can run that code. And after that code has been run, we can look at the two values, best.x and minimum. It looks like the x value that gave the smallest value of f is 0.25. Looks reasonable based on our graph. What is the value of f at an x of 0.25? Well, I kept track of that with the value minimum. Apparently that's 9.89. Let's just verify that by plugging in best.x into there. We see 9.894 here. Great. All right, last question of this activity, getting some more practice with if and for loops here. So we're going to find x and y to be the following vectors. We'll load up survey 09 and define x to be the values inside the weight column and y to be the values inside the desired weight column. What we're being asked to do is to define a vector called smallest and to go through basically element by element of these two vectors x and y and to store the smaller of those two values. We're going to create a vector called smallest. The first element of smallest is going to be the smaller of the first elements of x and y. The second element of smallest is going to be the smaller of the two elements of the second element of x and the second element of y, etc. So perfect use for a for loop because we'll loop through every single element of the vectors x and y. And a perfect example of when we want to use an if statement because depending on which of these two values is bigger and smaller, we're going to store one value or the other. All right, So how can we go about doing this? Well, my recommendation when dealing with for loops is to get it working for a particular example and then generalize that so that it fits in a for loop. So let's do that. Let's imagine we're looking at the 36th element of the x and y vectors. So let's just print those out to the screen so that we see what we're dealing with. So in this case, they're exactly equal to each other. Bad example. Let's go ahead and look at the next one. Exactly equal. Well, this is awkward. Exactly equal. Come on. Someone has to have a different desired weight than their actual weight. There we go. So 200 is the smaller of these two. So let's go and write code that's going to work for this pair of values. So what we're being asked is to find basically the ith element of that vector smallest, in this case, to be the smaller of these two. So I can't just simply left arrow it because it's going to depend on which one is actually smaller. I can't say it's equal to xi without actually checking to see is xi smaller than yi. So I actually need an if-else statement. So let's write the if-else statement and fill in the pieces. All right, so what's my logical condition? What am I checking? Well, I'm looking to see, all right, is xi less than yi? If that's the case, then that element of x is smaller than that element of y. And I want to store in my smallest vector, specifically the ith element of that, the smaller of those two quantities, xi here. If this statement is false, then I evaluate what's in the curly brackets to the right of the else statement. In that case, I want to be storing the value yi because yi would be the smaller one. So the ith element of smallest is going to be equal to yi in this case. All right, so will this code work as is? It won't. Let's run it and talk about why. It gives me an error. It says object smallest isn't found. And that just illustrates kind of the importance of initialization. Here I'm trying to put into the ith element of the vector smallest a certain number, but R can't do that until it's aware that the vector smallest exists. So I'm going to go ahead and actually just initialize smallest as an empty vector. And now it's going to let me run that line here. If I print out what smallest is, I have pretty much all NAs because I haven't looked at the first, second, third, fourth, etc. element. But here is the 39th element of the vector smallest. We see it's the smaller of these two numbers. So we have a piece of code that works for element number 39 in our x and y vectors. All right, so let's generalize this into a for loop. So let's write the skeleton of the for loop and figure out what we need and what we don't need. All right, so what are we looping over? Well, we're looping through the elements of x and y. So I basically need to consider element number 1, then 2, then 3, all the way up to however many elements of x I have here. So what's the sequence? 1 up to 579. All right, it's going to be up to me what I name my indexing vector, the thing that goes to the left of in. Since I wrote this example code, basically defining I to be 39, I'm just going to reuse that here. All right, so do I need I left arrow anything? No, because the for loop's going to automatically left arrow I to be a value in the sequence as we move through the for loop. I don't need to print out either of these two to the screen. Basically, all I need is this line of code. If the ith element of x is smaller than the ith element of y, the ith element of smallest is going to be xi here, the smaller of the two values. Otherwise, it's going to be yi, the smaller of the two values. So, boom. If you look at smallest here, these are all the values of the smallest numbers that it saw when comparing weight and desired weight. And what we're being asked to do is report the average value of this vector. So we could just get a summary of this. To get the average, it's 145.5. We could get that with the mean if we wanted to as well. 145.525, and it turns out that this is such a common operation here, trying to find the smaller of two different vectors here. We can actually check our work here by running the command pmin. So what does pmin do? Well, actually exactly what we do right here. It takes two vectors, x and y, and it reports element by element what the smaller of those two vectors are. Pmax would give you the largest ones. So if I were to look at the first few elements of head of pmin xy, this gives me the results of the smaller of those two quantities for the first 6 positions. And if I just print out, all right, well, what's the first few elements of the smallest vector that I've defined manually, well, it is the exact same list of numbers. So my code is correct, and I'm happy there. And there we go. Some good practice writing some if and for loops. That concludes activity 3.